In section 3.8, we will learn how to find the derivative of inverse functions and also how to figure out the derivative of logarithms. We'll also see that exponential functions are in here, and of course that's because it's the inverse of a logarithm. So do recall this simple fact about inverses, that given a function's graph, the graph of its inverse is reflected over the line y equals x. And we see this illustrated with these two linear functions below. This dashed line is the line y equals x, and we have a function f of x equals 1/2 x plus 1, the blue one right here, and its inverse, f inverse of x equals 2x minus 2, the yellow function right here. And again, you could go ahead and verify their inverses if you would like. We're asked to calculate the derivative of each of these functions, and let's see what we observe when we do that. So f prime of x is a linear function, so when we take its derivative, we're just going to get 1/2 plus 0, or just 1/2. Then if we consider the derivative of the inverse, well, it is also a linear function, and of course the derivative of the inverse function 2x minus 2 is just going to be 2. What do you notice about these numbers? Well, they are simply reciprocals. So here's our first observation, that the function and its inverse, their derivatives are reciprocals. But we have to be careful of one thing when we're talking about the inverse. Let's look at that on the next slide. The thing to note about a function and its inverse is what happens between the x and y value. And that is to say, they switch. So if we were to go ahead and state the formula for the derivative of the inverse, let's say we want to go ahead and consider the derivative of the inverse at b. Well, its derivative at b would be the reciprocal of the derivative of the original function, but being careful to make sure it's at the corresponding point, a. Of course, a is just, of course, the same thing as plugging in b to the inverse. Let's go ahead and look at this in a few examples. So let's use this idea, and we have something slightly more complicated here, but this will illustrate the idea of corresponding points. So consider this function, f of x equals x squared, where x is greater than 0. And of course, remember that this right here, this x greater than 0 part, needs to be needs to be here so that the function is 1-to-1. Remember, a parabola in general does not have an inverse because it does not pass the horizontal line test. But when you restrict it to the first quadrant, you do have the domain of just positive x's, and therefore you have something that is 1-to-1, and its inverse is square root of x. So we could go ahead and find these directly, but let's go ahead and just verify that with the idea of the reciprocal of the corresponding points. So the first thing to note is, why are they corresponding points? So you could go ahead and look at just what is f of 2, no derivative here. F of 2 is going to be 2 squared, which is 4. So the ordered pair we're looking at, the AB is going to be 2, 4 for if we're looking at f, or if we're looking at f inverse, the point we're looking at is it's the inverse, so it'll be switched. So f inverse for 2. And of course, we'll just want to go ahead and verify the reciprocal, this relationship between the derivative of the original at 2 and the derivative of the inverse at 4. So let's go ahead and see that. So f prime of 2, well, this is, let's go ahead and find f of x first. So let's go ahead and just find f of x, and let's take its derivative is going to be just 2x. So you can see right here it's going to be 2 times 2, which is going to be 4. And now let's go ahead and look at the derivative of the inverse function. The derivative of the inverse function is 1 over 2 square root of x. And again, this just comes from the fact that x to the 1/2 is another way to write the square root of x. And notice that we could go ahead and just do f inverse at the corresponding point, which is 2, and plug that into the derivative, and we get 1 over 2 square root of 4, which gives us 1 over 2 times 2, which gives us 1/4. So again, how are these related? Reciprocals, but do pay attention that we are looking at corresponding points for this to be true in every case. So again, this one wasn't too bad because we could easily figure out the inverse from the original function, but that may not always be the case. So let's look at this next slide where we have something that's a little bit tough. So for example, this one right here, if you try to find the inverse, so let's say we have y equals x cubed minus 3x squared minus 1. This, of course, is making sure that the function is 1-to-1. Well, if you were to exchange x and y and then try to solve this for y, it would be really quite difficult. So in this case, you wouldn't be able to do it, you wouldn't be able to verify directly. But look what we're asked to go and do. We're asked to go ahead and find the derivative of the inverse at x equals -1. So the thing to note that this is the corresponding point to this x value. If we're looking at this x, this is the x value for the inverse, and then 3 would be the corresponding y value for the inverse. So if you were looking at the original function, 3 would be the x value and -1 would be the y value. But we're going to focus on this top one because we're asked to go ahead and consider the derivative of the inverse. Okay, so how do we do this? The derivative of f inverse with respect to x at x equals to -1. Well, I don't have the inverse, so what I'm going to go ahead and do is apply that formula or equation from the previous slide or two slides ago. So that is to say, I have to consider the reciprocal, and I have to consider the derivative, the original function's derivative, evaluated at f inverse of -1. Okay, well, f inverse of -1, well, that is going to be the x value of the original function, or the y value of the inverse. So that's 3. So let's go ahead and just write this as f prime of 3. Well, and f prime is something we can easily compute. F prime of x could be computed just by using our given function. So f prime of x is 3x squared minus 6x. Well, we have f prime now. Let's just plug in 3, and that will give us the desired value. That is to say, we have 3 times 3 squared minus 6 times 3, which is 1 over, this is going to be 9 times 3 is 27 minus 18. So 27 minus 18, which is just going to give us 1 over 9. So while we could not compute the derivative of the inverse directly, we could go ahead and easily find the derivative of the original function, but just remembering the idea of looking at corresponding points, that we don't want -1 as the input to the derivative. We want the corresponding y value from the inverse or the associated x value in the original. So that is how we would go ahead and figure out the derivative of the inverse. Now this can help us find some general formulas. So let's go ahead and look at specific families of functions in the last slides of this. So the natural logarithm function, y equals ln of x. Well, we could really do this 2 ways. I'm going to go ahead and just show how we just did it with that formula, but we'll really find that some of you may prefer it even just to understand it in terms of implicit differentiation. So let's go ahead and just use that formula from the last slide first. So, okay, let's before we do that, let's just slide this down. Let's kind of take note of what we have and what we know. What we know so far is f of x, if we consider that as e to the x, its inverse is going to be ln of x. And we also know that the derivative of e to the x is e to the x. But what we don't know is the derivative of ln of x. That's what we need to figure out. So if we were to use that formula, we actually have everything we need to figure out f inverse of x prime. And again, there was a little mistake there. This should be, let's see, zoom in right here to fix that. That should be -1. Okay, so how do we figure this out? Well, this is going to be the reciprocal of the derivative of the original function evaluated at f inverse of x. Okay, well, notice f inverse of x we have, that is just ln of x. So it's going to be 1 over f prime of ln of x. Oh, what is f prime? We know that. That is going to be 1 over e to the ln of x. And well, if we notice that ln and e are just inverses, or these are inverse functions, we have 1 over x. So we actually we've just found the derivative of ln of x. The derivative of ln of x is 1 over x. So that's important to take away. So again, summarize, where did we get this from? Well, the formula, we know that the derivative of the inverse is 1 over the derivative of the original function evaluated at the inverse. The inverse of e to the x is ln of x, so that's where that came from. And what is the derivative of e to the x? Is e to the x. So that is why we take ln of x and plug it into e to the x. These cancel because they're inverses, and we have found the derivative directly using the formula. Maybe that's a little counterintuitive for you. You could also approach the derivation of this derivative by just using implicit differentiation. So how would you do that? Well, you would first just note y is equal to ln of x. And then, well, we don't know how to take the derivative of ln x, so what we could do is we could think about this as we could just change it to its exponential form, where you could just exponentiate both sides, just saying, okay, this side I'm going to apply e to, and then we have e to the ln of x here. So this is e to the y, and then this is just going to be x. Well, we can now take the derivative of this. If we take the derivative of the left-hand side and the derivative of the right-hand side, the derivative of the left-hand side, well, what's the derivative of e to the x? It's e to the x, but in this case we have y times y prime. And then the derivative of x is 1. So now solve for y prime. This is the same method we did on the last chapter. We have 1 over e to the y. Oh, y is what we have right up here in the original. What is y? It's ln of x. So this is 1 over e to the ln of x. And just like before, we cancel and we get 1 over x. So we now know the derivative of ln of x is 1 over x. So this is one more derivative to add to our toolbox. Let's go ahead and do a few examples of this just so we can see it in play with maybe the quotient rule, product rule, chain rule, or just other functions that we know how to take the derivative of already. Of course, I would encourage you to maybe pause and just try these first if you're feeling confident. But of course, if you're unsure, let's go ahead and just talk through a few examples. All right, so on this first one, we're asked to find the derivative of ln of 2x. So think about this. What do I have? Okay, this is a composition function. So that means I need to use the chain rule. Where my outer function is ln of x, so I know the derivative of that is 1 over x. And my inner function is 2x, and I know the derivative of 2x is 2. So now let's go ahead and take the derivative of what we're asked to look at. The derivative of the outer function is, well, 1 over x, in the case that I was x in there, but it's 1 over 2x because we're going to leave the inside alone. But then we have to multiply this by the derivative of 2x, which is going to be 1 over 2x times 2. The 2's cancel, and we have 1 over x. Interestingly, whenever you are taking the derivative of ln of x, the constant doesn't matter. And you may be thinking, well, why is that the case? And again, maybe just a quick little review of what's happening. Remember that you could write ln of 2x as ln of 2 plus ln of x. Well, if you were to take the derivative of this right here, what would happen? This right here is a constant. ln of 2 is a constant, so that is 0 plus the derivative of ln of x is 1 over x. So that's another way to approach that problem where you don't even use the chain rule. So this one is similar, a little bit more complicated. Do remember that we have no corresponding rule for addition, so see how this was multiplication. We were to break it up using expansion there. We do not have the same rule there. So this one we will need to go ahead and use the chain rule for. All right, so what is our outer function? Our outer function is ln of x, so the derivative is 1 over x. What is our inner function? Well, it is going to be x squared plus 3. And when I take the derivative of that, it's just 2x. Well, let's now use the chain rule to figure out the derivative of this one right here. Okay, the outer function is ln, so the derivative is 1 over x, but it's not just x here, it's leave the inner function alone. And now we need to multiply this by the derivative of the inner function. The derivative of the inner function is 2x as we computed on the right. So this is going to be 2x over x squared plus 3. You can see, now that you've seen one on how to use the chain rule with ln of x, let's go ahead and do one more problem involving the chain rule on the next slide. And again, I would encourage you to maybe try this one first. Pause the video and just see if you have an idea. Just kind of see if you can collect your thoughts, and then go ahead and see if you're able to understand my solution. So the thing to realize is that we actually have 3 functions here. Our outermost function is ln of x, and its derivative is 1 over x. Then inside of there is the squaring function, because again, we can take maybe one step just to add some clarity that we have cosine of x inside, yes, but before we consider cosine, we consider the squaring function. So our second function inside is x squared, its derivative is 2x. Then finally, cosine of x is the innermost function, and that derivative is negative sine of x. So if we take the derivative this time, we'll have to apply the chain rule twice. So here we go. I'm gonna keep a nice flow to this one now that we've gotten more comfortable with the chain rule. Outer function, ln of x. Well, the derivative of ln is 1 over, but instead of just x this time, we have this inner function of cosine squared of x. Okay, now I need to multiply this by the derivative of the inner function. The derivative of the inner function is 2 times cosine, and of course the cosine is the innermost function, so this one just comes along one more time. And then lastly, we multiply by the derivative of cosine, which is minus sine of x. Of course, clean this up a little bit. The negative and the sine and the 2 and the cosine all stay on top. So we have negative 2 cosine of x times sine of x. And then in the denominator, you have cosine squared of x. Well, and again, if you notice, this cosine cancels with one of the cosines in the denominator. So we actually have minus 2 sine of x all over cosine of x. Oh, and you may even notice, wait, sine over cosine, well, it is sunny today, so we might as well get a tangent. Therefore, we have the derivative of minus 2 times tangent of x is the simplest. So now that we know how to deal with the ln of x, we kind of have dealt with e to the x and ln of x as inverse. So let's go ahead and actually step back and talk about the more general exponential function. So the derivative of a general exponential function. So let f of x equal a to the x, where a is a positive constant, and I really should say other than 1. Other than 1, because of course 1 to the x is 1, so that is a constant function. So that the derivative of that one right there is just going to be 0. So how would I approach this one? Well, let's go ahead and actually turn this into something we already know how to deal with. I'm going to rewrite a to the x as e to the ln of a to the x. Okay, let's just go ahead and make sure we understand that really quick. Zoom in, just focus on that. Why can I do that? Why is this equivalent? Well, remember what happens between e and ln. They cancel, leaving you with a to the x, which is what we have right there. Okay, why did I do that? Well, because now that this a to the x is inside an ln, the power rule, not the power rule, the exponent rule, or it's the power rule for logarithms allow this to come out. And again, that's in a few slides from now. If we just remember, the power rule for logarithms allows the power of the input to come out in front of the logarithm. So that's what we're using there. Well, that means we can rewrite this as e to the x times ln of a. And again, just one thing, remember, ln of a is a constant as well. So that's going to be useful in helping us find the derivative. We don't need the product rule here. And I know this looks like a product, but again, just think about ln of a as a constant. So how would you take the derivative of like 2 times or x times 2? Well, this is the same thing as 2 times x, and that's derivative of 2. So no need to use the product rule. Just go ahead and just realize what we are looking at is a constant times x. So now how do I take the derivative? Well, I'm going to go ahead and just then realize the derivative of a to the x with respect to x is the same thing as the derivative of e to the x times ln of a. So this right here is my inner function. So the derivative is e to the x times ln of a times the derivative, so I'm going to do this in red to match above, times the derivative of x times ln of a. What is the derivative of x times ln of a? Well, it's just going to be ln of a. So let's see what we have right here. This is e to the x times ln of a times, now kind of on the same level as e, ln of a. Notice we really actually have some nice symmetry right here. We have found the derivative. Let's just do one more step to clean it up though. This right here, e to the x ln of a, is what we have here, which is the same thing as a to the x. So the derivative of a to the x with respect to x is just going to be a to the x, but instead of nothing there like e to the x, you have ln of a. So this right here is our general derivative for the exponential function. And the thing to maybe note, just we've really been working with this already. Let's just consider an example before we get to something more related to this specifically. Notice if you were to go ahead and let the base be equal to e, well, what you have is the derivative of e to the x is e to the x times ln of e, and that just is going to cancel with the power of 1. So it's e to the x times 1, which is e to the x. So it's what we've been dealing with already. But now that we know that the derivative of a to the x is just going to be a to the x times the ln of the base, let's go ahead and look at it in a few examples. All right, so we have 3 to the x right here. It's an example of an exponential function with base 3. How would I approach this? Well, first of all, it is important to note that this is an exponential function. Honestly, there's nothing fancy here. We just are going to apply the rule. So the derivative is going to be 3 to the x times ln of the base, which is 3. We're done here. But there's a lot of mistakes that could happen. The one thing that I see pretty commonly is a temptation to use the power rule. So the one thing to note is do not use the power rule. What do I mean by that? The power rule is only used when you have something like x, so some of your variables in the base, and a constant in the power. We have the base is your constant and the variable is in the power. So this is not the exact same thing as a power function. This is an exponential function. So if you were to write something like x times 3 to the x minus 1, this is not the derivative of 3 to the x. This is honestly just wrong. So make sure you're careful with that. That 3 to the x prime, or the derivative of 3 to the x, you cannot just apply the power rule. You have to go ahead and use the exponential rule we just figured out. All right, so that's one thing to know. This next one is a very basic chain rule. I would encourage you to try it. Pause the video and try it. Okay, our outer function is 3 to the x. We know that that derivative is, well, we just found it over there. It's going to be 3 to the x times ln of 3. Inner function is minus x. Its derivative is minus 1. Now, using the chain rule, we have 3, but not x this time. We have an inner function of minus x, so just bring that along, times ln of 3, the base. And then let's go ahead and just color that red. We still need to take the derivative of the inner function. The derivative of the inner function is minus 1. So our final answer here is minus 3 to the minus x times ln of 3. That is our derivative. Let's just do one more example. Actually, 2 more examples. I forgot I had 2 here. So let's do 2 more examples. This next one, again, it's just a exponential function with a trigonometric function inside. And the one on the right is going to be an exponential function as your outer function, and your inner function is a power function. So again, remember, you can rewrite this, and again, we're just using a different variable occasionally to keep ourselves comfortable with it. 5s, and then that s is to the 1/2. Okay, give those a try. Pause the video to see if you can do it, and then go ahead and hear the explanation. Okay, so this derivative of 3 to the sine x, your outer function is exponential, your inner function is trigonometric. So it's going to be 3 to the sine x times ln of 3. And now I need to multiply that by the derivative of sine. The derivative of sine is cosine of x. honestly, that's as clean as it could get. So this right here is our derivative, just recognizing what is our inner function is sine of x, and the chain rule causes you to multiply by the derivative of sine, which is cosine. The one on the right here, well, the derivative of the outer function, again, is exponential, so it's going to be 5 to the square root of s times ln of the base. Now we have to multiply this by the derivative of the inner function, which is 1 over 2 square root of s. You could rearrange things a little bit here to have the denominator underneath and the blue terms on the top. Is 5 square root of s, this is an s, times ln of 5 divided by 2 times the square root of s. So now that we have the derivative of our general exponential function, let's go ahead and find the derivative of our general logarithmic function, where the logarithmic function in general is just its inverse. So you have really a couple ways to go about doing this. The easiest thing to do is just to kind of use the change of base formula. Recall the change of base formula is that you can rewrite any logarithm with any base in terms of another base. Most commonly, you would rewrite it as ln of x, where this x comes from here, and this a comes from whatever the base of the original log was, and this right here is entirely up to you. We're just using ln because it's something we know how to take the derivative of. So just like before, we really should say that a is a positive constant other than 1. And what we could go ahead and do is rewrite the logarithm, log base a of x, as the quotient of two natural logarithms. So you'd have ln of x in the top, then you would have ln of a in the bottom. So again, remember, this ln of a is a constant. So whenever you're multiplying by a constant, you really just ignore it and you just multiply that in to your derivative afterwards. Maybe just to see a quick example again, then I'm going to kind of write it over here. The derivative of, let's say, 2x squared, let's do that, is going to be 2 times the derivative of x squared, which is 2 times 2x, which is 4x. So with that in mind, I'm going to have this 1 over ln of a, which is a constant in front. Then we'll multiply this by the derivative of ln of x. Oh, we know that. That is just going to be 1 over ln of a times 1 over x. So most commonly, we have the derivative rule for a general exponential function written like this. The derivative of log base a of x is 1 over x times ln of a. Just rearranging this, the x typically comes in front of the ln. All right, so that is our rule for general logarithmic functions. Let's go ahead and use this in a few cases just to see how it works. All right. Again, if you are confident with it, maybe just pause the video, try these, see what happens, see if you can get it right. But if not, let's go ahead and hear the explanation. So our outer function this time is the logarithmic function, and the inner function is the linear function 5x. So the derivative of the outer function is going to be done first. So that's going to be 1 over, instead of x this time, you're just going to bring the inner function along. So this was x in the general formula, but it's 5x in this context because it's a little more complicated. Times ln of what? 5? No. It's ln of the base, or ln of the base, so in this case 2. But now we have to multiply it by the derivative of the inner function. The derivative of the inner function is 5. So our answer here is 5 over 5x times ln of 2. 5's cancel, giving you 1 over x ln of 2. There's another one. Again, remember, this right here, this x ln of 3, you don't need the product rule. ln of 3 is a constant. Think about this as just like 3x. You wouldn't need the product rule there. The derivative would just be 3. Okay. Again, maybe now that you've seen one, pause it, see if you can do it. So to take the derivative here, note the base is all about that base. It's all about that base. Okay. It's going to be 3. So we have the derivative is 1 over the inner function, which is 1 times x ln of 3 times ln of the base. The ln of the base is, well, 3 in this case. So now this right here should have been a plus, so let's fix that. That is going to be a plus. So this is my inner function. I still need to take the derivative of this because of the chain rule. And we have 1 plus ln, here, I'll just write it like this first. X ln of 3 prime, so I haven't taken the derivative yet. What is the derivative of 1? Well, that is 0. And the derivative of this right here is just ln of 3, because again, ln of 3 is a constant, and then a constant times x, this derivative is the constant. Rewriting this, we would have ln of 3 in the top, and then you would have 1 plus x ln of 3 times ln of 3. Notice we have a common ln of 3. We can cancel that because this is multiplication and the parentheses has the 1 plus x ln of 3 grouped. So our final answer here is 1 over 1 plus x ln of 3. And because we were using 3 so much there, we're going to do a third example. Another one involving 3. I'll give you this one for free. All right, so what is our outer function? What is our inner function? So our outer function here is 3 to the x. It's exponential. So when I take the derivative of this, so the derivative of 3 to the x, just remember, is going to be 3 to the x times ln of the base, which is 3. And our inner function here is log base 2 of x, which is a logarithmic function, obviously. And the derivative of log base 2 of x, well, pause and see if you remember it. It's going to be 1 over x ln of the base, which in this case is 2. So we now have our functions and we know how to take the derivative separately. Let's go ahead and do this in the context of the chain rule. So, and again, I'm doing a lot of the chain rule because it's where I see the most difficulties of in understanding. As you get in the homework, you'll have to use product rule and quotient rule with these as you gain mastery. Okay, so the derivative of the outer function, this time is going to be exponential. So it's 3, bring the inner function along, times ln of 3. That is just the derivative of the outer function. Now we have to multiply it by the derivative of the inner function, which in this case is going to be 1 over x ln of 2, as we wrote over here on the right. And honestly, let's just kind of rearrange things, clean it up a little bit. We have the 3 log base 2 of x. That is to be the numerator. We can multiply that by ln of 3. And then in the denominator, you have x ln 2. So this is our final answer. Now, these logarithmic functions are very useful. It allows us to take some complicated things and break them apart into pieces using the algebraic properties of the natural logarithm. Remember that the product of 2 arguments inside of an ln, you could break each argument to be the input of its own ln with addition. Similar idea with quotients, except for subtraction. And again, just remember that ln of, let's just maybe remember that ln of 1 is 0. Because if you consider the natural logarithmic function, it has an x-intercept right there at 1, 1, 0. So that you could even kind of imagine that's where we have just minus ln of x, and we talked about the power rule earlier. Now, the logarithmic differentiation is a technique where we go ahead and essentially use logarithms, natural logarithms most typically because they have the nicest derivative, to break apart something really complicated. So if you really want a challenge, go ahead and try to take the derivative of this. You would have to use the product rule and the quotient rule and even kind of consider the train rule right there. So it's just a lot happening. So what we could go ahead and do instead is we could go ahead and take ln of both sides. So we could rewrite the left-hand side as ln of y, and the right-hand side is of ln of this whole quantity right here, x squared plus 1 times x plus 3 to the 1/2 all over x minus 1. Now, we do have some restriction here. That is to say we have to consider values of x greater than 1. If you need to use logarithmic differentiation at this point, you will really have that kind of set up for you given. But the reason being is, and you may have caught it, when you think about a logarithmic function, its domain is only in the positive. The domain is 0 to infinity, so this is just a shift happening. So we just have to be aware of that. Can't plug in 1 either, because then you would have 0 in the denominator. So why did I do that? Well, let's leave the left-hand side alone. The reason I did that is on the right-hand side, we could rewrite this whole right-hand side as a bunch of sum and differences of logarithms. So anything in the numerator is going to be positive. So this is a positive ln of x squared plus 1. That x squared plus 1 belongs to that first logarithm. The 1/2 right here comes down in front, so plus 1/2. And then we have ln of x plus 3. And then this x minus 1 is in the denominator, so you could rewrite this as ln of x minus 1. So we still have something equivalent to our original function. It just is much easier to take the derivative of this. Now, there is one catch, as we'll see when we take the derivative. You have to remember implicit differentiation. That is to say, the derivative here of ln of y is 1 over y times y prime. Remember, when you take the derivative of something that it's not your variable, so we're respecting x here, we have to multiply it by y prime in this case. So the derivative of the next term is going to be 1 over x squared plus 1 times 2x. ln of x is the derivative is 1 over x, but of course, keeping in mind chain rule here, the derivative of the inner is 2x. Then we have plus 1/2 times 1 over x plus 3. Again, the derivative of x plus 3 is just 1, so if you want to write that just to see it for now. Then you have minus 1 over x minus 1. And again, times 1, the derivative of the inner function is 1. And remember, implicit differentiation, you have to solve for y prime. So in the simplest form, y prime is going to be equal to 2x over x squared plus 1 plus 1 over 2 times x plus 3 minus 1 over x minus 1, all of that times y. Technically, this should stay as a function of x, so instead of writing y, we should go ahead and multiply this by our original function, x squared plus 1 times x plus 3 to the 1/2, all of that over x minus 1. So you can see it's what we have right here could be cleaned up. You could distribute, do all sorts of cancellation, which you would naturally get when you do the quotient rule and the product rule. But this is indeed the derivative. So this is an example of logarithmic differentiation. It's another tool that allows you to find derivatives of especially complicated functions using techniques that are a little bit simpler. All right, we have one more type of function to look at, and it's something we really haven't worked with much before. Shows up a little bit more in Calculus 2, and it would be the function x to the x. This is referred to as a transcendental function. Transcendental. There we go. Yeah, I'm just making sure I spelled that right. Wow. It transcended my spelling. I don't know. Okay. Transcendental function. The reason it's transcendental is because notice this is not a power function because the base is a variable. That's okay, but the exponent is a variable as well. So it's not a power function. It's also not an exponential function because the base is not constant. So the way we're going to do this is using that same technique as before, zooming in really quick right here. Notice again, if the n goes on top up here, you would have that x to the n back. And then the L and the E would cancel to give you back this right here. So it's that same move we did earlier. And what it allows us to do is to go ahead and rewrite this as a in terms of functions we know how to deal with. So x to the x is the same thing as x to the, oh, hold on, let's get this right. It's e to the ln of x to the x, which is, of course, the same thing as e to the x times ln of x. So this top right here, this quantity is just a product rule. But now we can take the derivative of this. So if we were to take the derivative of ex to the, or e to the x times ln of x, we would have, well, derivative of the outer is e to the x times ln of x, just e to the x is e to the derivative is e to the x, so that comes along, times the derivative of the inner function. The inner function, we do need a product rule here because, again, x is a variable. Before it was like ln of a, so you would just have this as your derivative, but we need the product rule. So, notice this thing right here is what we got here, which is the same as x to the x. So we'll just rewrite that as x to the x right now. Then the product rule right here is going to be first times the derivative of ln of x, which is 1 over x, plus the second times the derivative of the first. The x's cancel, so maybe in the simplest form, the derivative here is x to the x, and then we'd have 1 plus ln of x. All right, and one last thing that we will see, and it really just kind of shows up here because we've dealt with e so much. You'll explore this more in Calculus 2, but one way of approximating e is writing it as a limit. So this right here is another way of writing the e. And again, this is something you'd explore more in Calculus 2 as you get into sequences and series. But in this lesson, we have learned how to go ahead and take the derivative of inverse functions. We then use that to figure out the derivative of ln of x. We then figure out